Okay guys, let's take a look at today's lesson. It's alternating series day 2. One of the topics that students tend to have difficulty with is the error or remainder. And so we're going to look at this type of error or remainder, the ones with alternating series. We're going to continue to look at it, hopefully to get you very comfortable with the concept of error. When we get to the next unit on Taylor series and power series, error is a big factor in that unit as well. So it's just, I want to get you used to talking about error. Let's talk about this specific kind. This is for alternating series, and if we have a series that has terms that are alternating, decreasing in magnitude and have a limit of 0, that should be very familiar to you, right? We talked about that yesterday. If it's alternating series, if it's alternating, decreasing in magnitude, and have a limit of 0, then it converges. Right? That hopefully is familiar. And it has a sum, S. Now typically, to find the exact sum is difficult, so what we do is we do approximations. And this is the way that this is working. So if the sum S is approximated by the nth partial sum, for example, maybe we want to add up 6 terms of the sum and get an approximation for the actual for real sum. Then the error in the approximation is written like this, absolute value R sub n. Now R means remainder, and remainder means error. They like using the word remainder for error. It's basically the leftover part, the part that's not exact. They use that, so you need to be comfortable with knowing that R sub n means error or remainder. The actual word is remainder. This is just another way to write the error. S minus, so S stands for the actual for real sum minus our approximate sum, S sub n, however many terms we added up. That's going to be less than the absolute value of the first omitted or truncated term. Okay, so let me translate that for you into just regular words. That means the absolute value of the first omitted or truncated term, this is really meaning the next term. Those are fancy math words for meaning the next term. So if I added up the first 6 terms, then my first omitted or truncated term would be the 7th term. It's the next term. This is also called an upper bound. So we're going over vocab words right now. This is the upper bound of my error. So vocabulary words important. They may ask you for the upper bound. They're just talking about this. Find this value. All right. So, in other words, if we have the 3 conditions that are met, you can approximate the sum of the series by using the nth partial sum, S sub n, and your error will be bounded by the absolute value of the first truncated term. Okay, that's the absolute value of the next term. Okay, so that's the concept behind the error that we're going to be working with today. In order to use this theorem, this alternating series remainder theorem, the alternating series actually has to converge. So you need to mention that it converges. You can't just start using it on any alternating series, because it doesn't work on any alternating series, only those which converge. Okay, questions so far? That's just the concept we're going to be looking at. We're going to look at some problems. Okay, let's go to the next page. All right, example 1. We're given this series. They want us to approximate the sum S of the series by using its first 4 terms. All right, so let's do that. There's a couple ways you could do that. You could write the actual sum is about. You could write that notation. If you don't like that, you can write S sub 4 equals, that's my 4th partial sum. They want us to use the first 4 terms. And so I did that, and we get the first term I'm just going to use this notation as 1. The second term is negative 1 over 2 factorial. The third term is plus 1 over 3 factorial. Then we have minus 1 over 4 factorial. So this sum, we're approximating this sum. It ends up being 5/8. Or if you want to write it with equivalence, the fourth partial sum is 5/8. Okay, so that's our partial sums. Now part B says explain why the estimate found in A differs from the actual value by less than 1 over 100. This wording usually really confuses people. Like, what are they asking for? What they're asking for is for you to find your error bound and prove that your estimate is within this value. They're asking you to find the error. Okay, when they're asking you to do this, explain why the estimate differs, they're asking you to find the error. Okay, so let's do that. And in order to use our remainder theorem, we have to show that this converges. Okay, so to converge, we would say since the terms, number 1, alternate, number 2, decrease in magnitude, and number 3, the limit is 0, then we can use the concept that we learned on the other page. Now I'm going to write down 3 different ways to show error. This is one way you'll see it. Absolute value error. That's one way. Another way you might see it is with the R, and we're doing the fourth partial sum, so you might see it as absolute value of the remainder, the fourth remainder. Or you also could see it S minus S sub 4. S means that's the actual for real sum. S sub 4 is our attempt at our approximation of the sum. Now the reason that I'm writing these all up here is so that you're familiar with the way that you would see it. You certainly don't have to write them all up there like that. I just want you to see all of these expressions mean the same thing. Now, this one, actually, the AP guys like this one. You might see that one more often than the others, but you just need to know that all that means is error. So the little formula that we were looking at in the other, we said it told us that our error is going to be less than the first truncated term. And in this particular example, the first truncated term is the 5th term. So right now I'm just writing it symbolically. We're going to put numbers with it in just a moment because I want us to understand conceptually what we're doing. We're saying that our error, absolute value of the error, is going to be less than the absolute value of the 5th term. So now let's put some numbers with it. I'll just use this first one. You can use any of those representations you want. So the theorem tells us that the absolute value of the error is going to be less than the 5th term. And my 5th term is 1 over 5 factorial. So now let's write that without the absolute value on the number. So my error is going to be less than, let's see, 5 factorial, what is that, 120. This is according to the theorem that we just looked at, that the absolute value of the error is going to be less than the absolute value of the next term, in this case the 5th term. And what they're wanting us to show is that error is less than 1 over 100. So does that make a true statement? Yeah, that's all they're wanting. This is what they're wanting right here. They're wanting us to come up with that inequality. Now part C is asking us to explain why the sum can't be 0.7. So estimation is a really big deal. especially the higher up in math you go. It's a really big deal. And so this theorem is, I mean, it's been tried and it's exact. I mean, it's going to be true. So if I know that my maximum error is 1 over 120, then can I find a range for the real sum, for the for real sum? I can, right? I can take my sum and do what to it? I can add the 1 over 120 to it, and that would be the very biggest the sum could be. And then I could subtract the 1 over 120 from it, and that would be the smallest the real sum would be. It's giving me an interval for the actual for real sum. It's narrowing it down for me. So that's what we need to do here, is we need to find our interval of the real sum and see if this falls in our interval. That's what it's asking us to do. So I'm going to write it up symbolically first. So S stands for the actual for real sum. And in this particular instance, what I would do is I would take my fourth partial sum, which I calculated, and I would add my fifth term to it. And on the other side, I would take my fourth partial sum, and I would subtract my fifth term from it. So symbolically, that's what we're going to do. Now, you don't have to write that on your work. I'm just showing you what we're just looking at. What actually am I doing? Conceptually, what am I doing? So now let's put numbers with it. So my real sum is going to be between, so S sub 4 is 5/8, so 5/8 plus 1 over 120, and I'm just going to give a decimal equivalent or approximation since this is in decimal, is 0.633. And then if I subtract the 1 over 120 from it, I'm going to get 0.617. And that tells me that the real sum of this series is somewhere between 0.617 and 0.663. Does that allow this to be the sum? It doesn't. It doesn't fall within that interval, does it? So that proves that that can't be the sum. So since this is the case, we would say, therefore, the sum cannot be 0.7 because of our interval. What if we wanted to get a better approximation? What would we have to do to get a better approximation? Right now, I mean, we're pretty close. 0.617, 0.633. What if we wanted to be close to like the tenths or the thousandths? What would we do? Yeah, we just add more terms, right? We would get more terms because the farther out we go, the smaller this term is going to be, right? Our error, our bound will be smaller. All right, because these converge. They're decreasing in magnitude, they alternate, decrease in magnitude, and the limit is 0 because the ones that this works on, they converge. All right, okay so far? All right, the last one, we are looking at how many terms are needed to approximate the sum of the series so that the estimate differs from the actual sum by less than 1 over 100, and then it wants us to justify. So there's a couple of ways to do this. I'm going to show you just pretty much straightforward, probably the easiest way to do this. And there's another one on your daily work that you'll have to do a little bit differently. But let's work this one just by, let's start approximating our sum. Let's start writing out terms. So if I put a 1 in there, I get a 1. If I put a 2 in there, I get minus 1/16. If I put a 3 in there, I get 1 over 81. And what am I looking for? What significance does this play? I want my term, my next term, to be smaller than this. I want it to be better than this. Okay, so far, let's look. Then the next term is 1 over 256. All right. So, do we have the number of terms that we're going to need? Let's think about this. So we want the next term to be a better approximation than 1 over 100. So how many terms do I need? I need 3. Okay, so I stop here. Okay, and some people refer to this as stop and chop. It's a strange saying, I know, but maybe that'll stick in your head. I don't know. So we're going to stop, and then we're going to cut off the rest of it. So what we have discovered is that 3 terms are needed to achieve this, for our estimate to differ from the actual sum by less than 1 over 100. And now we need to justify. Okay? So part of the justification needs to be that this is actually a series that converges. Right? We need to say that. So just like over here, we say since the terms are, number 1, alternating, 2, decreasing in magnitude, and 3, the limit is 0, then my error, remember we have 3 ways to write error. Oh, that'd be a great formula question, wouldn't it? What are the 3 ways to write error? A formula quiz question. Error is less than our 4th term, which is negative 1 over 256. The absolute value of our 4th term. Okay? So then to justify, we need to include this number in there. So then the error is going to be less than negative 1, oops, we're taking the absolute value off, so that's not going to be a negative, that's going to be a positive. So 1 over 256, which is less than 1 over 100. So our error. And that's our justification. Okay? Questions? All right.